The last talk of this session is Signature Restriction for Polymorphic Algebraic Effects. This paper is by Taro Sakiyama, Takeshi Tsukada, and Atsushi Igarashi. The talk will be presented by Taro Sakiyama.
Hello, I'm Taro Sekiyama. This talk is about our ICFP paper, Signature Restriction for Polymorphic Algebraic Effect. In this work, we consider a new type-safe approach to combining two programming features, algebraic effect handlers and polymorphism. Algebraic effect handlers is an approach to user-defined effect, and they can also structure effectful programs in a modular way, thanks to the separation of interface and implementation of effect. Using algebraic effect handlers, we can define the various effects, such as exception, backtracking, state, and interactive I/O. Another feature we consider in this work is polymorphism. In particular, we consider implicit polymorphism as a ret polymorphism. And by combining these two programming features, we can make not only expressions, but also effects polymorphic. Okay, so let's show the one example of using algebraic effect handlers and polymorphism. And algebraic effect handlers provide three constructs to implement the effect. The first construct is effect declarations, which is used in the first line of the running example. Here, the operation choose is declared with this polymorphic type. So this type means that the choose operation takes two arguments and returns either of them. Here, polymorphism allows the type of choose to abstract over the type of argument. The second construct is operation calls, which is used in these expressions. Here, the arguments to choose operation calls are first and second functions for pairs. So both of these functions can be of this polymorphic type. So the result of this operation calls is also assigned the same polymorphic type. The third construct is for define effect, and which is achieved by the use of effect handlers. So effect handlers are a key component in defining effects, but in this talk, I omit the details of them. So, so the problem we consider in this talk is that the naively combining algebraic effect handlers and implicit polymorphism. So this is a problem because the naive combination of these programming features makes statically typed language unsafe. This is because algebraic effect handlers have the ability to manipulate delimited continuations, but the naive combinations of the use of continuations and implicit polymorphism is known to be unsafe. So this is a problem we attack in this work. But this is a classic problem. So there are many approaches to solving this one. So the existing approaches can be classified into two categories. The first category is considered the restricting operation calls in polymorphic expressions. For the running examples, the approaches in this category restrict these expressions because this is an operation call in a polymorphic expression. For example, value restriction, weak polymorphism, closure typing belong to this category. An advantage of using these approaches is that they can address any effect, including ML style reference and control operators. However, disadvantage of these approaches is that they impose a restriction on any effect code. Because, for example, even if the operation code doesn't need restriction. For example, we found in the previous work, exception and backtracking don't need a restriction, but the approaches in this category don't distinguish effect that need a restriction and effect that don't need a restriction. So they impose a restriction for all effect. As a complementary approach in the previous work, we provided a new approach to restricting effect handlers instead of operation calls. So in the running example, this approach restricts this part, effect handlers. A good point of this approach is that it allows operation calls of safe effect anywhere, and it rejects unsafe effect safely. But the problem of this approach is that it is not clear how to mix the safe and unsafe effects in a single program. So this could be a problem. This could be a problem in the general purpose programming because we may want to use safe and unsafe effects in a single program. And to solve this problem, we propose a new approach which restricts the types of effect operations. So in these running examples, this new approach restricts effect declarations. And we can determine whether any usable effects are safe only by examining this type. Okay, so let me summarize our work. We propose a signature restriction, which can ensure safety of effect with polymorphism. And the signature restriction accepts only effect that can be safely used anywhere, even in polymorphic expressions, without any other restriction. The signature restriction examines the typed signatures of effect. So it is very simple criterion. But it is still permissive in the sense that it can accept many useful effects. And it is also scalable. It means that the signature restriction can easily support basic programming construct, including the products, sums, and list. And to show the correctness of this signature restriction, we provided a simple type system for algebraic effect handlers and polymorphism. We show soundness of the simple type system by assuming all effects satisfy the signature restriction. So this demonstrates the correctness of the signature restriction. But the problem with this simple type system is that we cannot use both effects that satisfy and don't satisfy the signature restriction. So to solve these situations, we propose an effect system where both safe effects and unsafe effects can be used. And more precisely, in this effect system, effect that satisfy the signature restriction can be used anywhere without restriction, but if effects don't satisfy the signature restriction, then they can be used only in monomorphic expressions. We also provide an artifact that implements a tiny, small, ML-like functional programming language where all effects are supposed to satisfy the signature restriction. And this implementation does not cover the effect system part. Okay, so this is a quick summary of our work. And next, I will present a brief overview of signature restriction. As I said, signature restriction is an approach to determine the safety of effect with a signature of effect. So let's suppose we consider these operations with this polymorphic type. Here, signature restriction determines the safety of effect only by examining the properties of alpha in argument type tau 1 and return type tau 2. More formally, we can say operation satisfies the signature restriction if and only if alpha occurs only negatively or strictly positively in argument type tau 1, and alpha occurs only positively in return type tau 2. Here, let me remember what does mean by strictly positively. So in this simple function type, the occurrences of alpha 1 and alpha 3 are positive, but only the occurrence of alpha 3 is strictly positive. This is because the occurrence of alpha 3 is reached by going through only the positive part of function type, but the occurrence of alpha 1 is reached by going through a negative part of function type constructor. So this is a difference of the probabilities of alpha 1 and alpha 3. And by using these definitions, we check the three operation calls satisfy the signature restriction. The first example is choose. So we can easily find this type of choose satisfies the signature restriction because for the argument type, the bound type variables occurs only strictly positively. And for return type, it also occurs only positively. So this choose operation satisfies the signature restriction. And we can apply similar discussion to the Fay operation. For the satisfy operations, this function, this argument type may seem complicated, but the priority checking is very easy. We can easily find that this type, in this type, the bound type variable alpha occurs only strictly positively. So satisfy operation also follows the signature restriction. And as a result, all of these three operations satisfy the signature restriction. Okay, so this is our work, but our work does not cover all useful features in functional programming language. For example, this work does not cover type inference and general algebraic data types. So the support for these features is left as future work. And we also considered studying CPS transformation for this restriction method and applying the signature restriction to other user-defined effect mechanisms, such as monas. It should be interesting, we consider. Okay, let me summarize this talk. The problem we attack in this work is that the naive combinations of algebraic effect handlers and polymorphism may be problematic. To solve these problems, we propose a signature restriction, which is a new approach to determine the safety of effect in a polymorphic setting. And the signature restriction rests only on the properties of bound type variables. So it is very simple. It's just examining the signature of an effect. And it is still permissive and scalable. And we provide a simple type system and prove its soundness by assuming all effects satisfy the signature restriction, and which demonstrates the correctness of signature restriction. And we also provide an effect system where both effects that satisfy and don't satisfy the signature restriction can be used. That's it. Thank you for listening.
Thank you, Taro. If you are watching this stream live, don't forget about the Q&A session that may be available in your time band so that you can discuss this work with the authors.